Right now, tonight, tens of thousands of rocks are quietly sailing past Earth. Almost all of them are cataloged, tracked, and frankly boring. Until one of them isn't. Astronomers and space agencies spend enormous effort tracking these so-called near-Earth objects for one very practical reason. They want to know, decades ahead of time, if any of them are actually headed our way. It is not paranoia. In 1908, an object exploded over Tunguska in Siberia and flattened 80 million trees across 2,000 square kilometers, with no crater and no warning. In 2013, a much smaller rock, only about 20 meters across, exploded over Chelyabinsk, Russia, releasing more energy than 20 atomic bombs and injuring around 1,500 people, mostly from flying glass. Nobody saw that one coming because it approached from the direction of the sun, exactly where our telescopes are effectively blind. So have you ever wondered how astronomers actually tell the difference between an asteroid and a comet, when both often look like nothing more than a faint dot crawling across a photograph? The textbook answer is simple. Comets grow a glowing tail of gas and dust as they swing close to the sun. Asteroids made of rock and metal do not. Halley's Comet is the classic example, a dirty snowball that lights up spectacularly every 76 years and has been recorded by human civilizations for over 2,000 years. But here is where it gets strange. In the last few years, astronomers found a handful of objects that break that simple rule completely. They show absolutely no visible tail, no coma, nothing a telescope can see. And yet, their orbits drift slightly off course, as if some invisible hand were gently nudging them. Scientists gave the strange, in-between group, an equally strange nickname. They call them dark comets. Until recently, only 14 of these objects had ever been identified anywhere in the solar system. The most famous puzzle connected to this idea is not even from our own solar system. In 2017, astronomers spotted an object called 1I Oumuamua, the first confirmed visitor from interstellar space. Oumuamua was unlike anything seen before, elongated, tumbling, and moving on a hyperbolic path that could only have come from outside our solar system. And it did something nobody could fully explain. As it left our solar system, it sped up slightly, in a way gravity alone could not account for. No tail was ever detected. So scientists were left with two competing explanations. Either sunlight was pushing it like a very inefficient solar sail, or it was quietly venting gas from ice nobody could see. That debate never fully closed. And it turns out Oumuamua may not have been some cosmic one-off. It might have been the first hint of something hiding much closer to home. Researchers studying near-Earth dark comets have split them into two families. Inner dark comets, small objects only tens of meters across, orbiting close to Earth itself. And outer dark comets, hundreds of meters across, following wide, looping paths shaped by the gravity of Jupiter, the same kind of orbit followed by classic Jupiter family comets. For one of these outer dark comets, astronomers eventually dug up old images from a solar observing satellite and found, buried in the data, actual visible activity the object had been hiding from everyone. So what if the answer to that Oumuamua mystery was never really out in interstellar space at all, but right here in our own solar system, hiding in plain sight this whole time? That question leads us to an object catalogued back in 1998, with the unglamorous name 1998 SH2. For 27 years, 1998 SH2 was about as ordinary as a near-Earth object gets. It orbited the sun, occasionally swung close to Earth, and generated absolutely no headlines. On paper, it was just another asteroid, a dark, roughly 380-meter chunk of rock, about the length of 3 football fields laid end to end. Then, in August 2025, something happened that had never happened before in nearly 3 decades of watching this object. To understand why that mattered, you need to know how planetary defense actually works day to day. Telescopes across the world scan the sky constantly, feeding positions into shared catalogs. But for objects passing especially close, astronomers bring out a much more precise tool: radar. Powerful dishes like NASA Goldstone antenna in the California desert can bounce radio waves off an asteroid and measure its exact distance and shape. Radar is how we know the detailed shapes of famous asteroids like Bennu and Apophis, cratered, lumpy little worlds, some shaped almost like spinning tops. On 26 August 2025, Goldstone pointed precisely where 1998 SH2 was supposed to be, based on 27 years of tracking data. And it found nothing. No echo. No signal. After 40 minutes of searching different frequencies, the team gave up and moved on to a different target. Have you ever had a GPS confidently send you down a road that simply is not there anymore? That is roughly what just happened to a team of professional astronomers, using one of the most sophisticated tracking systems on the planet. 5 days later, a telescope in Brazil finally relocated the object visually, and the news was stranger than anyone expected. 1998 SH2 was 153 arcseconds away from where the math said it should be. To put that in perspective, that is a deviation of 19 times the expected margin of error, a gap far too large to blame on a simple measurement mistake. Something, somehow, had been quietly steering this asteroid off its predicted path. So here is the real question this story is built around. What do you do when a rock you have tracked for almost 3 decades suddenly refuses to be where the math says it should be? The team, led by David Farnocchia at NASA Jet Propulsion Laboratory, went back to the data and tried adding one extra ingredient to the orbit calculation: a small transverse push, the kind of gentle shove you would expect from gas escaping off a surface. That single addition fixed everything. It explained the missed radar detection, and it let the team successfully catch 1998 SH2 with radar just days later, on 2 September 2025. But the size of that push was 10 times larger than anything sunlight alone could produce through the so-called Yarkovsky effect, the subtle thermal nudge that affects every asteroid in the solar system. 10 times too strong for sunlight meant only one real explanation was left standing: outgassing. Ice turning directly into gas and leaking out from beneath the surface. Exactly what comets do. So the team pointed some of the largest telescopes on Earth at this supposedly ordinary asteroid. The 6-meter Canada-France-Hawaii telescope caught it first, a faint, low-brightness tail stretching about 20 arcseconds. Then the European Southern Observatory's 8-meter Very Large Telescope in Chile confirmed it with an even longer tail, extending to the southwest, clear and unmistakable. For 27 years, this object had been quietly leaking material into space, so faintly that no survey on Earth had ever noticed. The dust in that tail told its own story. The grains were unusually large, up to 600 micrometers across, far bigger than the fine haze typical of most comets, and they were released in a short burst between late August and early September, weeks after the object's closest pass by the Sun. That delay is a clue in itself. It suggests the ice doing the venting sits buried below the surface, insulated enough that heat takes weeks to work its way down, similar to what has been measured on Comet 67P, the target of Europe's Rosetta mission. Altogether, the object was releasing roughly 1.2 septillion water molecules every single second, more than enough to explain both the trajectory shift and the visible tail. Following the discovery, the Minor Planet Center gave 1998 SH2 a dual identity. It now carries both its old asteroid designation and a brand new comet name, P-1998 SH2. This is the first time in history that a hidden comet was found in this exact order, predicted mathematically first, from nothing more than a wobble in decades of tracking data, and only afterward confirmed by pointing a telescope at it. And that order matters, because there are roughly 2,000 known near-Earth objects sharing the same kind of Jupiter-shaped orbit as 1998 SH2. Researchers now suspect a meaningful fraction of them could be unrecognized comets too. Of those, 285 are officially classified as potentially hazardous, meaning their paths bring them within about 5 million kilometers of Earth's orbit, and they are large enough to matter if the classification is wrong. That is not just bookkeeping. Comets and asteroids do not move in quite the same way, and a comet's outgassing can nudge its future path far more unpredictably than gravity alone would suggest. That unpredictability matters enormously for anyone modeling long-term impact risk, or planning a deflection mission like NASA DART, which in 2022 successfully rammed a spacecraft into an asteroid just to change its orbit slightly. There is a deeper implication too. If a meaningful number of these quiet, dark objects are holding onto ice, they may belong to the same population that delivered water to Earth billions of years ago, back when our planet was still forming. For now, the impact risk from 1998 SH2 itself remains zero for the foreseeable future. But the method used to unmask it may soon reveal that the solar system has been hiding a lot more comets than anyone ever assumed.